All right, everyone. Today, Dr. Freericks is going to be lecturing on quantum mechanics and quantum computing. Dr. Freericks is a professor at Georgetown University and has been since 1994. And he's worked in a lot of different areas in physics, including condensed matter, quantum computing, of course, and so on. And please give him your full attention for the next hour and a half.
Okay, good.
All right, great. Well, I hope everyone can hear me. Thank you very much for inviting me to this. And I'm glad to see that we're finally able to do this because we've had a number of issues with scheduling and so forth that have made it very difficult to actually have this take place. And even though I got COVID about 2 weeks ago, that's not stopping us from doing this. Otherwise, I would have been there in person with you. So the title of my talk is When Will Quantum Computing Be a Big Deal? I know many of you have heard about quantum computing. You might be wondering at what point in time am I going to be able to go to a store and buy a quantum computer? I'm going to tell you that's not going to be for quite a long time. But even before that, when is quantum computing going to do something that's really useful? And that's really what I'm going to be talking about. So I want to start by reviewing a little bit about classical computing. This beast over here is the ENIAC machine, which is the first classical computer. And then this is a very old, I believe IBM, but it might be another, it might be Apple computer. How does classical computing work? It uses binary logic and it uses transistors. And this is an oscilloscope of a transistor. And it has two states. It has an off state and an on state. And they're fairly widely separated by voltage. So if I put a discriminator where that yellow line is, it's very easy to tell when it's on the on state and when it's in the off state. And this means that we're not going to have a lot of errors when we use this binary logic. And, you know, classical computing has gotten quite complex. The error rates are very low. There are billions of operations per second per CPU. And you can do a lot of things with it. So what does quantum mechanics have to do with computing? And where does that come in? Well, the first thing to recognize is quantum mechanics is about objects that are small. In fact, they're very small. And one of the questions you might ask is, how can I work with something that's so small I can't see it? In particular, could I do something to actually separate them according to some quantity that they might have? Well, you all know how to do this for one quantum object, which is light. You can separate light according to its frequency in a prism. You just shine white light through a prism and out will come the different colors of the rainbow from blue all the way to red. But what about something like an atom? How can I do a separation type of an experiment so I can work with different states of atoms? So some atoms behave like small current loops. And I'm not sure whether you guys have taken electricity and magnetism and actually talked about current loops. But when we talk about them from an atomic scale, we call this current loop behavior spin. And when you take a current loop and you put it in a magnetic field, a gyroscope is a perfect analog of a current loop. When you put it in a magnetic field, just like putting a gyroscope in a gravitational field, it will precess, and I'm showing you the motion of precession. But if you put it in a non-uniform field, it will also get pushed. And so when you put an atom in a non-uniform magnetic field, you can separate it according to how much it precesses or the magnitude of the spin associated with the current loop, which you can think of as an arrow. If you spin your fingers around of your right hand in the direction that the gyroscope is spinning, your thumb will point in the direction of the spin, which is the axis in this image here. So this experiment was actually done more than 100 years ago. It was done in 1922 by Otto Stern and Walter Gerlach. And this is a postcard that they sent to Bohr. This is what you have without a magnetic field. And with a magnetic field, it's separated into two different categories for the atom, which correspond to two different spin states. And there's a very interesting story where someone claims that the fact that these guys like to smoke cigars that were cheap cigars that were high in sulfur helped them actually see this imaging because they were using silver atoms. And with the sulfur, the beam of silver atoms on their glass substrate would become much darker if it interacts with sulfur. So here's an animation of how such an experiment would work. We have this current loop, which is indicated by the arrow that's spinning around, and then that straight arrow is an indication of the effective spin. It's going through this inhomogeneous magnet, which is indicated with this red and blue object. And you can see when it gets into the magnet, it precesses, but it also feels a push. You can't really see the push until you let it go far enough away, because we gave it some momentum in that horizontal direction that it gave a push. And by measuring where on this screen it hits, I can tell you what the projection of that spin was. So if I had a classical collection of these current loops, I would expect to see a pattern that looks like this, where I have all different possible values ranging from a maximum value to a minimal value. Now, when we do the experiment on a quantum system, and I'm indicating that for you with these spheres because we don't know whether it has a current loop in it and how it's oriented because we can't really see it. What we find is, unlike the classical experiment where we should get all possible values, we only get two values. Now, this is kind of an odd result. So if I look at changing the angle of the magnetic field and run the experiment again, I still get two values, and they're the exact same magnitude. So if you thought of this as the projection of a vector, if I went perpendicular to the direction of the vector, I should get zero projection. But indeed, we get the same projection regardless of what direction we put the magnets in. That is, of course, weird. The quantum Stern-Gerlach experiment separates atoms into only two possibilities. So a question is, can we use this just like a binary 0 and 1 for computation? The first thing we want to ask is this a reproducible experiment? And so to talk about that, I'm going to package this device that I just told you that has the magnet here that separates into the two paths into a device here that we're going to call a Stern-Gerlach analyzer. And it's packaged to look like this. That's the direction of the magnetic field. The fat arrow indicates that it's increasing in the upward direction. That's the positive projection, and that's the negative projection. And there's only two outcomes that I can get when I send a beam of atoms through this device. So to check to see if it's reproducible, we'll just take the output from the positive result and send it through an analyzer again. And if it's reproducible, everything should come out the positive exit again, because I selected only the ones with a positive projection. If I measure it again, I expect it to be positive. And indeed, this is what happens. We find that these experiments are completely reproducible. Once we have separated the atoms, they remain separated and they preserve the quantum number that we separated them with respect to. So we have a well-defined bit that is exactly one of two values. Now, there's a wrinkle, however. If we take this and we put it through 3, where one is vertical, one is horizontal, and one is vertical, what you might reason is it's going to take all the ones that are positive on the vertical axis, and then we're taking all the ones that are positive on the horizontal axis. So these guys should be both positive on the vertical and positive on the horizontal, in which case they should all come out of the positive exit. But when we do the experiment, we find half come out the positive and half come out the negative. It's as if all the memory of that vertical projection has been lost. And I like to describe this as atoms being stupid. They can only remember the last projection that they were measured on. So if I measure them on this vertical direction, on this horizontal direction, they forget about whatever projection they had on the vertical. And the fact that something that has a horizontal projection comes out with a 50-50 split comes from the fact that you can actually write the quantum state in a particular way. So the atoms cannot have a definite projection in more than one direction. And if it has a spin up, it also has a left projection and a right projection 50% of the time. This is called superposition. It says that the state is not determined, it's indeterminate. And so we would write that as an upspin is half of the time pointing to the left, half of the time pointing to the right. And this is an amplitude, which is the square root of the probability. And so it's 1 over square root of 2 if it's 50% to the left and 50% to the right. So both expressions are different ways of describing the exact same quantum state. Now, the spin degree of freedom is used in ion trap computers, and these are actual individual ions that have lasers shown on them, and then they re-emit the light so you can actually see them, kind of like little lighthouses. Or if you ever read Dr. Seuss's Horton Hears a Who, these are like the little atoms telling you that they are here, they are here. And in these atom traps, you trap them and they have different kinds of normal modes. This is a center of mass mode. This is a breathing mode. And you can take these objects, they have these two states. We can use them in order to do computation. And I'm going to describe the kind of computation that you can use. So this is one form of a quantum computer. There's another one that's based on Josson junctions. I don't have time to describe all of what a Josson junction is, but it's a sandwich of a superconductor, insulator, superconductor object that has two quantum states that can also be manipulated like spins. Now, quantum mechanics is even weirder than what happens with superposition. That description that I showed you was kind of weird, but you probably are okay with it. There's another phenomenon that Einstein called spooky action in a distance. In 1935, he wrote a paper with Boris Podolsky and Nathan Rosen. Boris Podolsky went to the New York Times the day before the paper came out, and they put out, I think, a front page article saying how Einstein says quantum mechanics is not complete, even if it is correct. Einstein was livid about this. He was so angry with Podolsky, he never spoke to him again because he thought science takes place in scientific journals, not in the popular press. In the 1950s, Bohm came up with a simpler way of illustrating the same experiment using spins. He said, let's start with this state. So we have two spins here. One spin on the left, one spin on the right. In this case, it's a spin that is up on the left, down on the right. And in this state, it is down on the left and up on the right. But this is a superposition of those two states. It's not definite exactly what the state is until I measure it. And what happens now is if I let these two objects, these two spins, travel to the left and to the right, and then I measure them, what I'm going to find is half of the time I'm going to find an upspin in my detector, and half of the time I'll find a downspin in my detector. But what is very interesting is there's a correlation. When it's up on the left, it will be down on the right and vice versa. So each detector always measures randomly, half up, half down, but they're always correlated. And you might think that this requires some kind of signaling between these particles so they can tell, well, I measured up, so you better measure down and so forth. But quantum mechanics doesn't work that way. There's no need for any signaling. So it doesn't violate any kind of rules of special relativity, but some people like to call it spooky. And in fact, Einstein himself called it spooky. So Schrödinger named this, he called it entanglement, and Bell devised a way to test it. And Alan Aspect measured it in the 1980s, and he just won the Nobel Prize for this experiment. And entanglement is what everyone is excited about in quantum computing. This is where we can get an advantage. And I want to show you an example of how that works. So entanglement can lead to what is called quantum supremacy, which means I can do a calculation exponentially faster than I can on a classical computer. The simplest algorithm that shows this quantum supremacy is the Deutsch-Josza algorithm. It plays a game on a quantum computer, and it can show how to solve that game exponentially faster than if you played it on a classical computer. Now, I have to point out, computer scientists like to make quantum games. I have to tell you, they're not really games. They're not fun, but hopefully they will help us learn. So the game that they have is it constant or is it balanced? I told you the game is not fun. So we're promised that there's an oracle that will take an n-digit binary number and it will output a single one-bit number. That number will either always be 0 or it will always be 1. In that case, the function is a constant. Or half of the time it'll be 0 and half of the time it will be 1. In that case, it will be balanced. So the question is, how many times do I have to call this oracle before I can determine whether the function is a constant or the function is balanced? Now, if you think about this, if you just randomly call some numbers, most likely you don't have to call it too many times before you'll figure out whether it is a constant or it is balanced. But to make sure you're not incredibly unlucky and like it's balanced, but you just called it every time that it is 1, you have to actually call it 2 to the n minus 1 for an n-digit number plus 1 times to ensure that you know whether it is balanced or it is a constant. So that's an exponential amount of times based on the qubits, based on the bits in the number. And, we know that in general, you're not going to have that really bad case, but it could happen. And if you play the game enough, eventually it will happen. So there's this minimum of 2 to the n minus 1 plus 1 calls to be sure. The quantum algorithm requires us to call the oracle only once. And I want to go through carefully how that works. So we're going to illustrate with a 4-bit example. And these are the qubits that represent the number that we're going to be working with. And then we have an extra qubit that we call an ancilla qubit. This ancilla qubit will be initialized in the state 1, and the system qubits will be initialized in the state 0. And the first thing we do is we apply what's called a Hadamard operation. That takes each qubit to a superposition. If it's a 0, it takes it to a sum of a 0 plus 1. If it's a 1, it takes it to a difference of a 0 minus 1. And then there's this normalization factor that has to go in for the superposition. So after applying it on this state, because the initial system qubits are zeros, they all go to 0 plus 1, and you find you will get a linear combination of every binary number in this collection, all with plus signs in front of them, because it went to 0 plus 1. So if you like, you take 0 plus 1 multiplied by 0 plus 1 multiplied by 0 plus 1 multiplied by 0 plus 1, all as the digits, and then you find this number, 1/4 times the sum of these 16 terms. Now the ancilla, that was in the 1 state, so that one goes to 0 minus 1. So this will be the state on the quantum computer after we apply this Hadamard transformation to every qubit. Now our next step is to call the oracle, and we're going to use the oracle as acting on the ancilla. It's going to take whatever state, whatever number there is, and it's going to change the ancilla to the ancilla plus the function of x. This is how we're going to program the oracle in order to do what we want to do. Now, because f of x is equal to 0 or 1, when I add it to the ancilla, if it's 0, I just get the ancilla qubit, because 0 plus 0 is 0, 1 plus 0 is 1, so the ancilla qubit remains unchanged. But if it's equal to 1 and I add it to the ancilla, 0 goes to 1 and 1 goes to 0, because I'm doing my arithmetic modulo 2. And that will take the ancilla qubit and it will take this state and it will change it to minus that state. So I can summarize that, because f of x is 0 or 1, as minus 1 raised to the f of x acting on this state. It's really acting on the ancilla, but because it's multiplying the whole state, it actually acts, I can think of it as acting on the system. And this is a process that we call phase kickback in quantum computing. I found the phase on the ancilla, but I can actually associate the phase with the system. And you see the state x will now have a minus 1 if the f, the function for that state, is equal to plus 1. Or it will have a plus sign if it is equal to 0. Okay, so the state can now be written in this form. And at this stage, we've done everything that we need to do with the ancilla. It's going to just sit there. We're not going to play with it anymore. So we're going to focus on this state that we've created, which is minus 1 to the f of x multiplied by the state x summed over all of those terms. So again, if I go back to this previous one, the coefficients of each of these terms will be plus 1 or minus 1, depending upon whether or not f of x is 0 or 1. Okay, that's what this summation represents. All right, now, our next step is we apply a Hadamard again to the system qubits. And because 0 goes to 0 plus 1 and 1 goes to 0 minus 1, you have to actually sit down and carefully work this out. What you find is the state gets a factor that multiplies it, a minus 1 to the x dot y, where x dot y is written in this fashion in terms of the binary notation of the different qubits. So you have your initial state x, and you're going to take the product with the y state. These are just binary numbers that are zeros or ones. I'm going to add them modulo 2. So in the end, this is a number that's going to be 0 or 1. Okay, and the way that you can imagine this is that each xi is equal to 1. When it's equal to 1, the yi term gets multiplied by minus 1. And that's why this dot product here picks up all of the minus signs that you're going to have. Okay? Now, we're going to measure the qubits. And we're going to look to see, does it come out with the state 0, 0, 0, 0? What happens is if f of x is a constant, the coefficient of the 0, 0, 0 state, that corresponds to the case where y is 0, all zeros. So x dot y is going to just be 1, and I'm going to just have minus 1 to the f of x, summed over all of the possible values, the 16 values of this binary digit. Now, if f is a constant, minus 1 to the f of x is either equal to plus 1 or minus 1. But when I take the modulus squared of that, it becomes plus 1. If, however, it's balanced, half of the time it's plus 1, half of the time it's minus 1. When I add them all up, I get 0. So if it's a constant, I am guaranteed with 100% probability that when I measure the system, I will get the 0, 0, 0 state. If it is balanced, I am guaranteed I get some other state. So by doing this measurement, I can determine whether or not the function was a constant or was a balanced function with this one measurement. And remember, we only called the oracle once. Okay? So that's how you get this quantum supremacy. You essentially call the oracle once, but because you called it on a state in superposition, it was applied to all of the states at once. And then by cleverly rearranging your system in the right way, you can get the situation where you have an all or nothing probability. If I measure one state, I know the function is a constant. If I measure another state, I know that the function is balanced. Okay, so it's a pretty cool result. This is the way that you can get this exponential speed up. But I definitely would not call this game a particularly fun game. This is called quantum supremacy, and this quantum calculation is exponentially faster than the classical calculation. Now, it may actually turn out to be true that quantum supremacy will actually occur not because of these kinds of speedups in terms of operations, but instead because a quantum computer has a huge memory advantage over a conventional computer. And I'm going to sort of talk about that in the second half of this talk. This is what I expect for many scientific problems, and I want to describe to you how that's going to work. I'm wondering whether this is a good time to potentially have a break and see if there are questions, because I'm kind of at the halfway point. I'm not going to make it through the rest of the talk before 3:05. What do you guys think? What do you want me to do?
Here's my question. Raise your hand.
So I am having a little bit of trouble hearing, so you'll have to repeat whatever question is asked.
Yeah, there's one question you should do. Just say it to me and I can do it. One person asked, what is the oracle?
That's a very good question. So when Deutsch-Josza created this problem and showed that it has quantum supremacy, they did not show how you make the oracle. So what the oracle does is the oracle is going to implement the function in this following way. Whatever x is, the oracle knows what f of x is. So you have to implement a way for the oracle to calculate what f of x is. They say nothing about how that is done in their algorithm. They just assume that there's an oracle that will do that. And then you take that f of x and you add it to the ancilla qubit. This is the way that you implement their algorithm. So they are completely agnostic about how you would actually code up an oracle. And for many computer scientists, when they're talking about quantum advantage, they will ignore some of the potentially very complicated questions of whether or not such an oracle can be made, how you would make it, how it exists, and so forth. And this is something that they don't really address. They just assume that it can be made and their analysis.
Does anybody have any more questions? Ellie?
Could you talk more about the relationship between quantum and
I can't really hear you. You have to talk loud.
Yeah. Could you talk more about the relationship of entanglement?
I couldn't quite hear that. Is something about entanglement?
Could you talk?
Somehow I'm not picking up what you're saying. Can you stand closer to the computer and repeat it? Because right now I'm not hearing anything anymore. I'm not hearing anything that you guys are saying. Or you can type it in the chat. But I'm not hearing anything in the room anymore. It's just gone quiet. I see there's a chat now. Okay, so could you talk more about the relationship between quantum entanglement and quantum computing? Sure. So what you see here in this algorithm, when we apply the Hadamard transformation, we create this state. Even though this state looks very complicated, it's a product state. So a product state is a superposition, but it's a relatively simple superposition. It can be created by applying an operation independently on each qubit. And the qubits aren't talking to each other. They are essentially completely independent of one another. You can factorize this into the Hilbert transform acting on each one of these qubits multiplied by each other. But once we do this operation, then what we have done is we have changed this superposition by putting in this number -1 to the f of x in front of each one of these different terms. And now it is no longer a product state, it is an entangled state. And the entangled state allows us to do things like run all of the calculations at once with only one call to the oracle and be able to find a way of reading off the results. So if all I was doing was working with product states, Those are very easy states to represent on a quantum computer because I sort of represent them in terms of each qubit separately. And each qubit only can take 2 states, but I can just work on each one completely separately. However, if I have an entangled state, if I have n qubits, I have 2 to the n coefficients in this expansion, and I need to know all 2 to the n of those coefficients. And so I've gone from something where I need 2 times n to store the state, which is a product state, to 2 raised to the power n, which is a much, much larger number. And it's that ability to work with complicated information that now is at the level of 2 to the n. That's where we can get the advantage on a quantum computer. Now, it requires you to figure out how to do that. There's no simple rules that tell you, oh, this is easy. I just will come up with a simple algorithm that will do what I want to do. It's not so simple. On a quantum computer, we can only apply what are called unitary operations. You can't even do addition easily on a quantum computer. So you have to really think carefully about how you would implement an algorithm on a quantum computer to be able to make it work successfully. But this is what everyone is excited about, is that when you work with entangled states, then you have this huge increase in the power of your calculation. Okay, so I think I have lost all audio in the room, so I'm not sure whether this is a time to take the break, and maybe we can figure out if we can restore the audio. Or is there another question? Because we still have like 1 or 2 minutes before the break time. I see there's something in the chat. Okay, great. So we'll take a break, and when we come back, I will talk about the how we can use the memory advantage of a quantum computer as opposed to using the ability to do this quantum parallelism, which is what the Deutsch-Josza algorithm talks about.
We'll be starting really shortly. But just as a brief introduction for those who weren't here during A block, today, Dr. James Frederick is going to be talking to us about quantum mechanics and quantum computing. He already did the first part of his lecture during A block, so you might be missing some things, so don't be afraid to ask questions. There'll be a questioning round at the end of the block. But yeah, Dr. James Frederick is a professor of physics at Georgetown University, and we're so lucky to have him today. Please make sure to meet them.
Okay, so for those of you who are new, who are coming in, what I talked about in the first part was I discussed what a qubit is in terms of an atom, which can be separated into 2 different states, which can be thought of as a binary 0 or 1. And then we discussed an algorithm called the Deutsch-Josza algorithm that shows a exponential speed up in the number of steps that it takes to run the algorithm. As I was ending that discussion, I was on this slide where I said that true quantum supremacy might actually occur because of the huge memory advantage that a quantum computer has over a classical computer. And at least this is what I expect is going to happen for most of the problems that are going to be solved on quantum computers that are science problems. So I love this picture, which kind of shows our current state of the art of quantum computing. We're at the bottom step of a very intimidating staircase. We have what is called noisy intermediate scale quantum hardware. This was named by John Preskill. This is quantum hardware that cannot be error corrected, so it is not what is called a fault tolerant quantum computer. So it has a fair amount of errors in a calculation, and the qubits aren't perfect, they're noisy. So they don't, when you ask them to do something, they don't exactly do what you ask them, but they do something that's close to what you ask them. And he asked the question, can we do real science on such machines? So to give you a sense of the kind of interesting real science that we can do on these machines, I believe we can do on these machines, I want to talk about ultra-fast phenomena. And the first example of ultra-fast phenomena is from almost 150 years ago, where Leland Stanford had a bet with someone that when a horse is galloping, it lifts all of its legs off the ground. And it was a $10,000 bet, and he paid this person, Edward Muybridge, $10,000 to prove that he was right. He was so confident that he would be right. It took Muybridge 10 years to set up a system of tripwires and cameras so that he could take pictures of a horse as it galloped by. And then when you run those images together, you get a movie. And you can clearly see that the horse lifts all of its legs up during a gallop in this movie. And the key is that in order to study this phenomena, which is taking place on a millisecond time scale, you have to have cameras that can take images on that millisecond time scale. And that's what took Muybridge 10 years to work out. So since then, we've gotten to much, much shorter timescales. In the 1960s, Edgerton from MIT came up with what he called a microflash technology, which could freeze things at a nanosecond timescale. And there are many wonderful images. This is an image of a bullet going through an apple, but he has many wonderful images of bursting balloons and other things like this. You can find many of these on the web. But recent research is now 1 million times faster. So we're talking about femtosecond timescales. This is the timescale at which electrons move around and react to electric fields in solids. And a femtosecond is such a short timescale. It's the time that it takes for a photon to travel a micron in distance. So it's a ridiculously short time scale, but that's the time scale for what it is called ultra-fast phenomenon. And this is typically looked at with what are called pump probe experiments. So you get a very powerful laser, you shoot it at your device with a high intensity, and you excite it to some excited state. And then with some time delay, you come in with a probe pulse that probes the system that you've looked at. And by changing the time of the delay time for the probe, you can then study how the system relaxes back towards equilibrium after you have hit it with a really big hammer. And a class of systems that are interesting to look at with pump probe experiments are driven-dissipative systems. These are systems that have a field that is applied to them, but they're also attached to some kind of a bath which makes them dissipate energy. And it's one of the frontiers of quantum mechanics. We still don't really know how to solve the driven-dissipative problem in quantum mechanics, but there are lots of ultra-fast pump probe experiments and non-equilibrium experiments on ultra-cold atomic gases that actually provide data on these systems. And the theory tends to be restricted to very short times on classical computers. We're just not able to go to long times. And so one of the questions that I ask is, could this be the killer application for quantum computers? So this is an example of a driven dissipative system. You can imagine having electrons at different lattice sites, which are these gray circles, and the electron can hop from one lattice site to another lattice site or back. But each lattice site is attached to a reservoir where the electron can go into the reservoir and another electron can come back onto the lattice. And so this becomes, if I turn on an electric field to try to drive the electrons to move from left to right, this becomes a driven dissipative system. And what is interesting is if I have non-interacting electrons, I can actually solve the problem exactly, which is this blue line. And then there are a series of approximate solutions called master equations, which are the red and the black lines. And you can see, while they're not perfect, they do a pretty good job of showing the behavior of the exact solution of this driven dissipative system. And the reason why we talk about master equations is that's a master equation is something that we can put onto a quantum computer. So how does it work? We start off with a system that has a Hamiltonian, and which means it's a system that's interacting, plus a reservoir that it is attached to. We then construct a master equation that integrates out the effect of the reservoir and just describes what happens to the system in the presence of this dissipation. From the master equation, we create something called a Krauss map. And the Krauss map can be immediately put into a quantum circuit. And this is an example of the quantum circuit for that problem that I showed you before. So it's a relatively simple circuit. It requires 3 qubits, 1 qubit for the system, 2 ancilla qubits. And this is the way in which it works. These operations here are reset operations. These operations here are rotations with very specific angles. And this operation here is a C-naught, a controlled knot operation. We ran this on an early quantum computer, and we got reasonable results out to a very small number of time steps. We could go about 5 time steps before the quantum computer just wasn't able to keep doing the calculation that we were trying to do because of issues with its noisiness and the way in which the computer was structured. But what we needed was an ability to implement this reset operation. And about 2 years ago, IBM introduced partial resets into their hardware. And we went from being able to do 5 steps to being able to do many, many more, which I'm going to show you in just a moment. So we look at something called the Hubbard model. So the Hubbard model has these lattice and I can have upspin or downspin electrons sitting on the lattice sites. When both an up and a down sit on the same lattice site, because they're electrons and they repel each other, there's a Coulomb energy, U. And then they can move from lattice site to other lattice sites. That's this thing called a hopping. And if we apply an electric field, the hopping takes this form as a complex amplitude. And then each site is coupled to a bath, as I showed before. So if we take the limit where we just turn the interactions off, then we have this simple circuit that it's even simpler circuit than the one that I showed you that will actually do the time dynamics of this. And this is the result of going through that procedure, integrating out the reservoir, finding the master equation, getting the Krauss operators, converting it to a quantum circuit, and so forth. And now this is what we were able to do. This is 2,000 time steps. So we went from barely being able to do 5 time steps to being able to do 2,000 time steps. And if you look carefully at this data, you can see the data here and the data here look about the same. There's really no loss in the ability to run this data on the quantum computer. We could essentially run this data forever. Now, there are some issues. The fact that the data doesn't come all the way down to the lowest value here is because of decoherence in the system. And we introduce a number of multiple resets to extrapolate to the limit where there's 0 resets. And then we do a rescaling operation. And after doing that, we get these orange dots, which lie exactly on the black lines, which is the exact result. So this technique can be actually used to solve these problems very accurately, even on current machines. There's a stabilization of your quantum code that takes place when you're solving a driven dissipative system on these current quantum computers. We can use it to calculate the current that flows through the system. This is a plot of the current as a function of the strength of the electric field. This is a plot of the current as a function of time. And we're showing you data from some different times in the calculation with different amplitudes of the electric field. If the field is bigger, we have to run the simulation longer to get an accurate result. And a comparison of the quantum computing data, which is the blue, with the exact data, which is the black, shows you that this is actually working quite well. We're really able to get good quantitative data coming out of the quantum computer for these kinds of problems. We look now at a separate limit. In this case, we don't turn the U off, we keep the U on, but we turn the hopping off. So we have isolated systems that are interacting. And there are only 4 states that we have to look at: no electron, an upspin, a downspin, or an up and a down on the same site. And with this system, we ran another driven dissipative system. This one goes to a steady state. And a comparison of the blue, which came off the quantum computer, with the red, which is the ideal circuit, you can see in the long time limit, we almost get perfectly what the result should be. But we have some errors initially. But what is so nice about this circuit, and it's a more complicated circuit now, it's given by this circuit up here. What's nice about this is the errors go away if we run it for a longer and longer period of time. It's sort of a self-correcting circuit. And this is doing what's called quantum state tomography to show that the state really lives just on the diagonal of this matrix, which is what this state is supposed to be, just to make sure that we really are producing the right state. So we have this question now, how we found the NISQ machine killer application. This is a problem that's very hard to solve on a conventional computer, and yet it looks like quantum computers can solve it easily. Now, there is a caveat. We don't yet know how to solve the interacting problem on a quantum computer, and that's an area of active research. One of the things that we work with, though, if we are able to solve it, is we want to work with something called a Green's function. This is probably something you have not heard of. You don't need to know any real details about what a Green's function is, except it will help us solve problems like analyzing these pump probe experiments. And there's an algorithm to calculate a Green's function. This is what a Green's function looks like. You have some quantum object at one time and another quantum object at a second time, and you want to calculate an expectation value of that object. And there's a old algorithm. This algorithm is more than 20 years old, called the Hadamard test, which says you start out with your system and your ancilla, you apply a Hadamard to your ancilla to create the superposition, and then you do a controlled operation of the A so that you only apply the A if the ancilla is in the 1 state. So we've gone from a product state to an entangled state at this point. And then you do your time evolution of the system, which is given by this U operator. You then do a second controlled operation of this B operator. And now, by measuring the ancilla, you can calculate this expectation value, which is what the Green's function is. So this is a circuit that we can use to determine the Green's function. But the problem is, during this time evolution of the system, the ancilla just sits there waiting until the next operation will be used on it. And this is a period of time in which the entangled state can decohere, and then you lose the ability to get the results of your calculation with this decoherence. And we've tried to run this on a quantum computer using these driven dissipative systems, and it doesn't work. It just kind of gives garbage. So we came up with a much better way of doing this, which is a robust way, where we apply that operator A, we then apply another Hadamard, we do a measurement, and then we do the time evolution, and we measure the operator B in the system. And in this case, there's no decoherence, and we get the exact same calculation of this Green's function. So we ran this on a quantum computer. The black lines are the exact results. The symbols are the results of the quantum computer. This was run on a continuum machine. And you can see it gets this Green's function really accurately. There are nice ways of calculating the Green's functions robustly for these driven dissipative systems, which then would allow us to do things like analyze certain kinds of pump probe experiments. Now, if we can find the way to extend this to include interactions, which we don't know how to do yet, then we can actually simulate dissipative physics and chemistry on quantum computers. And I think it's a very exciting moment. The moment we can do that, we will have applications in science that cannot be solved on conventional computers. So we're very close to being able to figure out how to do this. And that kind of concludes what I wanted to talk about. This is showing you how using the large memory, which will store that quantum state and will allow that state to evolve as a function of time, how that can lead to a quantum advantage in being able to solve problems that we can't solve otherwise. This is a picture of many of the people who have worked with me on these different projects over the last couple of years. I'm not going to go through and name them all for you because I'm pretty sure you don't know any of these people. And I'll just end in case you have an interest in looking at more things that I do. I do a lot of work on figuring out better ways of teaching quantum mechanics. So I have this website, quantum.georgetown.domains, that covers all of my different educational projects. I have a undergraduate quantum mechanics course that's offered on edX every fall. This is going to be offered starting in middle of August. And for those of you who are interested in learning what superposition, entanglement, measurement, and so forth are in quantum mechanics, I strongly encourage you to sign up for this class, Quantum Mechanics for Everyone. It's a 6-week-long class that's going to be offered starting June 18th. And I guarantee if you take this class, you're going to really understand conceptual ideas of quantum mechanics very, very well. Much better than most people who are even practicing researchers in quantum mechanics will understand these kinds of ideas. So I highly recommend, if you're interested in this kind of these kinds of systems, this kind of physics, that you take that course. That's really all that I have. I'm happy to answer questions. So I'm going to open up the floor to see if anyone has any questions. We had a little bit of trouble with my hearing the questions, so if that happens again, we'll have to put them in the chat, but the chat seemed to work well during last period.
If anybody wants to ask a question, I can repeat it back to you. Yeah, tell me.
Could you give a little bit more detail on how the robust, like, method works and like why it combats the capabilities and stuff?
How what method works?
The robust.
Can you give a little bit more clarification on how the robust method works and why it combats decoherence?
Yes. So the key with the old method was that you create this entangled state and it just sits during the time that it takes to run this time evolution on your system. This can be a very long period of time if you're running a long time evolution. And if you just have a qubit sitting because it's in a noisy environment, it's consistently decohering so that you lose the entanglement. You just don't have an entangled state anymore. You lose the entanglement, you can't do this measurement and get the Green's function anymore. So what we have found is that if you measure the qubit, you need to know what the result of the measurement is because that's going to play a role in constructing the Green's function. But if you measure the ancilla qubit immediately after you apply this A operator, then you can do your time evolution. Because you've already measured this qubit, it's gone from the system. There's nothing left to decohere because you've already determined what its value is. You then measure the B operator in the system after the time evolution, and it will give this exact same result. So the measurement at the end is different because I'm measuring in the system rather than measuring the ancilla, which gives me the result from the system. But it does not suffer from decoherence. And to describe this in any more detail would probably require me to try to show you what the different quantum states are. But the point is when you do a driven-dissipative system, you're typically evolving a mixed state. And this measurement, so you have to repeat the measurement many times to get this result. This measurement projects you onto that mixed state But you have to repeat it many times in order to properly get the right mixture in that mixed state so that you'll get an appropriate result for the answer. So it just ends up being a slightly different way of doing the calculation. It's not dramatically different. It's just a little bit different, but it works very well in these cases where you're looking at driven dissipative systems.
All right, thank you. We'll see if there are any other questions. Ellie?
Does this function have any relation to like Green's theorem?
Does Green's function have any relation to Green's theorem?
In some sense, yes. So they satisfy a differential equation that has a source term in it. And this is what Green did when he was solving electromagnetism problems. He came up with sort of a universal source, and then he solved the problem with the universal source, and then by integrating over the solution with that universal source, you can then convert it into the result of any source that you might have. So it has a similar mathematical structure as a classical Green's function would for something like electromagnetism. But it's a quantum object that is being constructed. So the rules for how you work with it and how you determine what it is and so forth are a little bit different because they use rules of quantum mechanics rather than classical mechanics in working out how they work out. But the differential equation structure is very similar. I think that's why they call them Green's functions.
All right, thank you for that. We'll see if anybody else has any questions. Yeah, Talon again.
Could you give more detail on why it's useful to actively simulate these driven dissipative systems?
Can you give a little bit more elaboration on why it's useful to, can you repeat the
Simulate the driven dissipative systems.
simulate the driven dissipated systems?
So this is the reality. So most interesting devices that we have are devices that work due to some nonlinear effect. So a transistor is a nonlinear effect. In a transistor, I am sending current through a device. To send the current through, I'm putting a field on it. But transistors don't live in a vacuum. A transistor is sitting inside some metal that is attached to other things. It's generating heat. I'm dissipating the heat in the system. Otherwise, I will burn my legs from my laptop because it's getting too hot and so forth. And so most problems that we care about for technology are driven dissipative problems. Things like semiconductor lasers are driven dissipative systems. Many of these driven dissipative systems don't require quantum mechanics to describe them, and they can be described with sort of classical rate equations. We don't need quantum computers for those, but the ones that require quantum mechanics to describe them, those are the ones that we actually have a lot of trouble figuring out how to describe them using classical computers. The problem is a very hard problem. So it's kind of the frontier of the knowledge in quantum mechanics of things that we don't really know. And that's why it's an interesting problem to try to figure out how to solve.
And I guess kind of related to that, I also have a question, like sort of what's the next step or what's the next thing that you're hoping to do in this area of research?
Well, one of the things we've been looking at is trying to see if we can figure out how to different ways that we can try to describe the driven dissipative system when it's an interacting quantum system. We haven't had a huge amount of success in it, but this is the area that we've been looking at. And one of the things we've been looking at is if instead of looking at a quantum mechanical reservoir. I instead have a classical reservoir. Can I make more progress working with a classical reservoir than I can with a quantum mechanical one? It turns out that the classical reservoir doesn't quite have enough degrees of freedom in it to really represent the quantum reservoir. But there still might be interesting things that we can do with the classical reservoir. So that's one of the areas that I've been looking at recently. But yeah, it's a hard problem, and we're kind of starting to try to come up with ideas of things to try.
Great, thank you. If there are any more questions or. Okay.
I will put up the websites again. Whoops. I'll put up the websites again for anyone who wants to grab them. Sorry, I didn't make QR codes, but if you take a picture, you can go back and go to the different websites.
Oh, I think Ellie might have one more question.
Hmm?
Who do you usually work with, like while you research the computer sciences?
Ellie's question was, who do you usually work with when you're doing these projects? Like, are they computer scientists or are they physicists? Or
So most of the people I have worked with are other physicists. I don't think I have actually worked directly with any computer scientists in the work that I've worked with. Some of the collaborators have been mathematicians, but the vast majority are other physicists. And chemists. I do some work in chemistry as well. And for those projects, I work with chemists.
great, yeah, thank you so much. So our classes end at 4 o'clock. So I think this would be a pretty good ending point. Thank you so much for being here and lecturing to us for our 8th period. I think your presentation was really good. I really appreciated the visuals. They really helped me understand it. Yeah, round of applause.
Well, thank you very much. It was a pleasure to be able to give this presentation for you.
Well, thank you very much.